Hi everyone, welcome back to the Solver Deep Dive series. This is an ongoing series where I explain different components of MILP and CPSAT solver. And in today's episode, we are going to discuss locks in MILP solvers. So let's get started. So in a MILP solver, we store many different types of information, and the idea is that that information is supposed to help us with the solving process. So locks is one of those types of information. So there are many other information. For example, we also store clicks, we also store pseudocost. So logs is something that we store per variable, right? So per variable, we store two different types of information, up logs and down logs. So what is logs? Logs is basically the number of constraints that are restricting the variable. So if you look at this constraint, for example, so this constraint is restricting the x from increasing. So that's why it's an up lock for x. And similarly, the same constraint is restricting the y from decreasing, and that's why it's a down lock for y. So unlike other information, for example, clicks and pseudocost, this information is very cheap to compute, right? So all we need to do is we have to go through the constraint matrix, look at the coefficients of the variables and the bounds of the constraint. If the coefficient is positive and it has an upper bound, that means it is an up lock for that particular variable. If it is negative and it has an upper bound, then it's a down lock for that variable. And similarly, we can flip the signs for what happens when the constraint has a lower bound. So equality constraints, for example, would act as both up and down lock for a variable. Right, so it is very easy to compute compared to all the other types of information. It's very cheap to compute. We just have to make one single pass through the constraint matrix, and you have all the up locks and down locks information for all the variables. And we are only interested in the number, right? So we don't care about which particular constraint is actually the up lock or down lock for a variable. And now the question is, when do we want to compute this information? So there are some problems about that. So the idea is that we want to compute it right after presolve, but then there are also some presolve rules that can also benefit from this locks information. So first of all, why do we want to compute it right after presolve and not before it? That's because in the presolve rule, we modify the constraint matrix quite a lot, right? So we sometimes remove some variables, we sometimes change the coefficients, we update the constraint bounds, some constraints become redundant, and lot of things are happening. So it is kind of trickier if we compute all the locks information before presolve, and then we have to maintain that lock information during the presolve. So that's kind of a harder thing to do, but some solvers do it. And now let's take a look at how this locks information is used inside the solver. So let's say we are in this kind of a setting where we are minimizing an objective, and let's say for a particular variable xj, the objective coefficient cj is strictly less than 0. Okay, so that basically means that we want to increase the value of xj. At the same time, we also notice that xj has no up lock. So in this kind of scenario, it is very easy to deal with xj. We want to increase it as much as possible, and there are absolutely no constraint restricting it to increase. So we want to fix xj to its upper bound. If the xj doesn't have any upper bound, then the problem itself is unbounded. So this part is fairly simple. This is called the dual fixing. And obviously you can do similar things if the signs are flipped. So for example, if the objective coefficient is positive and the variable has no down locks, then you will want to fix it to its lower bound. Yeah, but let's make this case slightly more complicated, right? So instead of 0 up locks, let's say now it has 1 up lock. So something like this. So where aij, let's say, is positive and the constraint has an upper bound. So now it's not as simple as fixing this xj to its upper bound, because there is one constraint restricting it. So we only count the number of up locks, right? So we don't know whether this constraint is actually imposing a tight bound on xj or not. So it might happen that this is a very loose constraint. Its imposed bound on xj is looser than its original upper bound uj. So in that case, we can still fix it to its upper bound. But let's focus on the more general case scenario where the constraint is somewhat tight. It imposes a bound on xj that is tighter than its upper bound. There still can be some tricks we can do. So let's take a look at some of those tricks that are done by hikes and skip. So hikes in this kind of scenario looks for a binary variable xi such that if xi is set to 0, then this constraint becomes redundant. So what do I mean by redundant? It basically says that xi you fix it to 0, and all the other variables to some of their bounds, either upper bound or lower bound depending on the coefficient, fix them in such a way that the rest of the expression takes its largest value. And when you do that, that largest value is already less than or equal to bi, so we don't really need this constraint anymore. So in this kind of scenario, it is fairly simple, right? So xi is fixed to 0, then we no longer have any uplocks. That means we can fix our xj to its upper bound uj. But what happens when xi is not taking the value 0? Let's say xi is taking the value 1. So in that case, this constraint is no longer redundant. There is a tighter upper bound on xj that is implied by this constraint, right? So we again fix all the other variables to their respective bounds depending on their coefficient, so that the rest of the expression takes its maximum value. We move all of that to the right hand side, divide everything by aij. So that will give us a new upper bound. Let's call it u prime j. So that's what we want our xj to be fixed to. Since we picked binary variable, there are only two cases, and we can actually replace xj in form of xi, something like this. So when xi equal to 0, xj will take the value uj, and when xi equals to 1, this uj will cancel out and xj will take the value u prime j. So you see, it's a bit specific case, right? So we have one uplock and we are going through all the other variables to see if any of them are binary variable. If there is a binary variable, then we have to verify that when we set this binary variable to 0, then this entire constraint becomes redundant. But apparently it happens enough that the solver explicitly has this kind of presolve rule. Skip also has a bunch of presolve rules that deal with this kind of scenarios where the objective is negative and there is exactly one uplock, or the opposite direction, which is objective is positive and there is exactly one downlock. So skip looks for a singleton continuous variable in this same uplock constraint. So the variable, instead of being binary, it is a continuous variable, and it only appears in just one constraint. That's why it's a singleton variable. So let's say for the example purpose, xi is such a variable. Now again, my goal is simple. I want to fix xj to its upper bound. But if I do it, then things can get complicated inside this constraint. But fortunately, I have this kind of a singleton continuous variable. That basically means that this xi variable does not appear in any of the other constraint. And let's say its bounds are such that it can compensate for whatever the damage was done by moving xj to its upper bound. So for example, let's say the coefficient for this xi is positive and we move xj to its upper bound, then we should be able to decrease xi to a lower value such that it is still within the bounds and this constraint is still satisfied. So in other words, this xi variable is compensating for this xj variable, and therefore we can fix this xj variable to its upper bound. So there is a specific presolve rule inside skip. It's called dual comp. If you have, let's say, two uplocks, then you have to go through both of those constraints and manually verify that xj can safely take its upper bound, or it can be replaced with a combination of bunch of other variables. For example, in this case it's a binary variable, but it can also be aggregated with some other continuous variable. Those rules can get more and more complicated if you have more than one uplock. So I haven't seen that in the solvers, but theoretically it is quite possible. So this is an obvious use case of locks inside presolve rule, but there are many other presolve rules that use the locks information in a different kind of way. So here we are looking at how the variable is restricted in a particular direction. But storing this up and down lock number is not just about how many constraints are restricting it, but it also tells us that how important that variable is. So for example, in skip, there is a presolve rule called sparsify matrix. So it is basically looking for equality rows that can be multiplied with a constant and then added to other equality rows. The goal is that we want to reduce the number of non-zeros from the matrix. So in this kind of presolve rule, the locks information is not directly used, but it is used as a proxy for figuring out which variables we want to target. So if the variable has more up locks and down locks, that means it is more complex variable. Many other constraints are restricting it. It might be easier to target those variables that has fewer locks. So we'll look at this kind of use cases later in this video where the locks are not directly used but rather used as a proxy for figuring out how important a particular variable is. So next we are going to look at how locks is used in the rounding part. So let's say we have some sort of an LP solution where the integer variables are not taking integer values. We want to round those integer variable values in either upwards or downwards direction. So that's where we can use locks information. So the obvious way is we can use something called locks guided rounding, which is we round the variables towards fewer locks. So if a variable has 3 down locks and 5 up locks, then we would want to round it downwards because there are fewer constraints restricting the downwards movement for that variable. So this is a specific type of rounding. There are many different types of rounding techniques as well. So one is obviously you can round things to the nearest integer. One is obviously you can round things in the random direction. So locks is not just used inside this locks guided rounding, but for the other rounding rules as well. So that is more like a default rule for all the other roundings. So for example, if a variable doesn't have any up locks, then we don't care about what the rounding technique is being used. We always round it upwards. Similarly, if the variable doesn't have any down locks, then we don't care about the rounding rule, but we always round it downwards. So in hikes, this default technique is used inside randomized rounding and in line search rounding. But before we round it in the random direction, we check if the variable doesn't have any up locks. If that's the case, then we always round it up. If the variable doesn't have any down locks, we always round it downwards. If the variable has both kinds of locks, then we go for the randomized round. Similarly, there is this line search rounding which basically deals with 2 points. So there is let's say one LP point and let's say there is an analytic center. The goal for this kind of rounding is that we want to find a point in this line segment. So we start with let's say alpha equal to 0, which is at this point, and slowly increase the alpha to go through the points along this line segment. Even in this case, we use this default rule. So if the variable doesn't have any up locks, then we round it upwards. We don't care where the alpha is in our search process. In hikes code, there is also this thing that if all the variables are of this kind, where it either has no up locks or it has no down locks, the problem itself is roundable. If that is the case, then every time we solve an LP, we simply just try to round it. So the variables with no up locks, we round it up. Variables with no down locks, we round them down. And we get a free feasible solution every time we solve an LP. But in general, problems are not like that. Most of the problems have complicated scenarios, general scenarios where variables have both up locks and down locks. So we tend to use this kind of locks guided technique for rounding. And that is sometimes used inside diving as well. So when we dive, we solve a bunch of LPs. So this is one of the rounding rule. And this kind of rounding rule is also used inside feasibility pump. Right, so feasibility pump deals with 2 sequences. So one which is LP feasible and the other one is integer feasible. So we solve an LP on this side, then we try to round it using one of these kind of techniques. Then we again solve an LP that is closer to this integer feasible solution, and then we again try to round it, and so on and so forth. The hope is that these 2 sequences will at some point of time converge. So in hikes, this kind of line search technique is used inside the feasibility pump, but in general, feasibility pump, any technique can be used for rounding, and locks guided rounding is one of the important candidate inside this kind of rounding rules. So in feasibility pump, hikes also uses the locks information when it is trying to set the objective coefficients for this LP sequence. Right, so the goal is that we want to stay as close as possible to this integer feasible solution. But notice that in this kind of rounding techniques, we use this default rule. So if the variable doesn't have any up locks, then we always round it upwards. So for this kind of variable, hikes would not set any objective cost. It will set the objective cost to 0. Same thing when the variable doesn't have any down locks as well. The logs information is also used in many other heuristics where the focus is on measuring how important a particular variable is. So let's start with diving, right? So we already saw that we use logs information when we are trying to round the solutions that are generated when we are diving. So when we solve an LP, we want to round the solution. That's when we use the logs information. But in diving, we also need to select which variable we want to branch on. So this is where we can also use the logs information, which is called logs based diving. So it is not usually as good as pseudo cost like diving, but the logs based diving can also offer an alternative, and it can be used as a heuristic, right? So we use the number of logs for variable selection. So we want to prioritize fixing the variables that has a higher number of logs. Now in general, you can just simply add the up logs and down logs and call it a logs based score. But in hikes, there is also a more special rule for ordering variables where they multiply the down logs and up logs. So obviously they add some epsilon so that if the number of down logs or number of up logs is 0, then the product doesn't become 0. That's something that we also do with pseudo costs. And that is also a way of generating this kind of a logs based score. So in hikes, there is also a local search type heuristic. It's called shifting. So it deals with two kinds of scenarios. So one is where there is at least one constraint that is infeasible. There is an assignment of variable, but for that assignment, there is at least one constraint that is infeasible. In this case, we want to find one random infeasible constraint and try to shift a variable either upwards or downwards. So what we do is we pick a constraint and then go through all of the variables that are in that constraint, right? And we evaluate both directions for all the variables. Either we try to shift it upwards or downwards. And this is how we score the variables if they are fractional integer variables. So the score is basically -1 plus 1 by number of opposite types of logs plus 1. So let's say we have a variable that we are trying to shift it upwards. Then the score will be -1 plus 1 by number of down logs plus 1. So if the variable has more down logs, then this fraction will be smaller and the score will be lower. And in this case, lower scores are better. So that variable has a higher chance of getting picked. If obviously the variable is not integer variables, then we don't look at the logs information, but we rather look at how it will affect the objective. And that's a different type of score equation, but we'll not focus on that for now. And then there is also another situation where let's say we are dealing with an LP feasible solution as a starting assignment. And in this case, there is no violated constraint, but rather some variables that are supposed to take integer values, they are not taking integral values. So that's kind of the similar scenario as the diving. And for that, we use this logs information, which is we pick the variable that has a higher number of logs. Finally, in skip, we also have this kind of a logs heuristic. So this is something that is similar to the clicks heuristic that we discussed in one of the previous videos. It is based on this paper by Gerard and others, that is structure driven fix and propagate heuristics. So the idea is that we want to sort the variables based on number of logs in a decreasing fashion. So higher number of logs we want to deal with first. We will fix those variables one by one and then propagate them. There is limited backtracking in this fix and propagate. If let's say about 65% of variables are fixed, then we solve the LP for fixing the remaining continuous variables or other general integer variables. So if this LP solution is also integer feasible, then we stop here. If it is infeasible, then also we stop here. But if it is LP feasible but not integer feasible, in that case we move on to the last step, which is we solve a submap. Since we have fixed so many variables, then hopefully this submap is easier to solve. So as I said, this is quite similar to the clicks heuristic that we saw in one of the previous videos. There we pick the variables that appear in larger clicks first and then do this fix and propagate, solve LP and solving the submap. So apart from this heuristics in hikes, there is a piece of code that basically orders all the integer variables based on the number of logs. So they generate log scores for all the variables by multiplying the number of up logs and down logs, and use that score for sorting all the variables. So any heuristic that requires going through all the integer variables, they don't go through the variables in the default order. They first sort it based on the number of logs. If the log scores are tight, then they look at the click scores. But that's the idea, right? So this logs information is the one that is mainly guiding how the variables should be considered in those heuristics. So let's quickly recap what we saw in this video. We saw how the logs information is used in MILP solvers. So for the presolve rule, we saw the dual fixing rules, which are fixing a variable to either its upper bound or lower bound based on the objective coefficient and the logs information. We also saw how the logs information can be used for guiding the direction in which we round the solution, and this rounding is used at multiple places inside the MILP solver. And finally, we also saw how logs is used inside other heuristics, where we use the logs information to find which order we should consider the variables in. So that's all for today's video. I hope you liked it. Please don't forget to press the like button and subscribe if you haven't already. That helps me grow this channel, and I will see you in the next video.